So we went over one of these in motor control. We can, but we don't control the speed with the voltage. Yeah, if we couldn't control the speed on it, we'd have problems with our air conditioning units. We'd have problems with if you got a ceiling fan, it's AC. Can you control the speed on that? Usually 3 speeds, right? Usually 3 speeds. So yeah, we can control the speed. So you're gonna run into a lot of single phase motors out there. What's the big advantage of single phase motors over 3 phase?
Oh, they cheaper.
Cheaper. They're a lot cheaper. Single phase motors are a lot cheaper. Single phase is cheaper than 3 phase as far as low wattage, very low power, very low horsepower motors. Single phase is a lot cheaper. Could you imagine if Alabama Power had to run 3 phase to all the houses out there? So we could run 3 phase motors.
I would like it.
I know you wouldn't. So anybody, but what problem do we have with single phase motors? What makes a motor turn? Magnetic field. But one of those magnetic fields got to move. So in AC, DC, of course, we create a shifted magnetic field with the commutator, right? So what we do is we keep switching the polarity on the armature, which causes the motor to rotate. Okay, so what we're doing with a DC motor is you're shifting that field with a commutator. Now 3 phase automatically creates a phase shift. Single phase doesn't. Because single phase, there's no phase shift in there, right? So what does that mean we have to do to cause a single phase motor to rotate? Well, we have to create a phase shift. So we create it with devices called either capacitors or inductors. Here's DC. This is our DC motors we went over. Oh, I'm going to set up a pulse width modulation thing here. So here's the way we reverse it, and then of course I need to come back to stepper motors. But AC motors, single phase. So single phase, we have capacitive start, we have capacitive run, we have 3 phase, 3 phase, we have Y delta, Y bound over. We have single phase motors. So we have devices in electronics we call capacitors. I don't know if I've got my circuit set up. It wouldn't take very long to do it. But what we can do with a capacitor is a capacitor is a really neat unit. A capacitor creates an opposition, but it doesn't do any work. So it does no electrical work. It doesn't. If it was a perfect capacitor, it wouldn't consume any power at all. So capacitors don't get hot because there's no current flow through them. The current flow is in and out of them. A good analogy that I use, if I can find it real fast, is a bucket. So if you could think of a capacitor like you think of a bucket. sure it would be in here. I do. I got a PowerPoint somewhere that I made. So it's good. Here it is. So this is the power, so we got a pump. You should have a resistor here, by the way. And all we do is, a capacitor's got two plates. And then all we do when we put AC on this thing is it does this. So notice there's no water flowing through the two buckets. And that's what a capacitor does. Thank goodness we use this technique all the time. There we go. And of course, what determines how fast the bucket fills up? Size of the bucket and how fast the water flows into it. So if we got the bigger the capacitor, the longer it takes to charge it. The smaller the capacitor, the faster it charges. Does that make sense? So what we do is really, really interesting is that when we put a capacitor, when we first put voltage on the capacitor that's discharged, it acts like an empty bucket and the water comes flowing in extremely fast. But as the bucket fills up, the water slows down until it tops out. So what happens is that when we have 0 volts across the capacitor, the current flow into its maximum. When we have full voltage across the capacitor, there's no current flow at all. So that's just opposite of a resistor, right? It makes sense. So the voltage across the capacitor and the current flow into it are 180 degrees out of phase. So it automatically creates a phase shift. Does that make sense? So if I can create a phase shift by 90 degrees, did I say 180? It's by 90 degrees. If I can make a phase shift, what we do is between an R and a C, we can create a phase shift a lot of different angles. So R does work, a capacitor doesn't do anything. So capacitors don't get hot, which is pretty. If you got a capacitor that's real hot, what does that probably mean? It's bad. That means current flows through it and something's happened to it. Normally what they'll do is they're sealed up real good, especially we call them electrolytic capacitors. They're sealed up real good and they'll actually bulge out on one side and they will blow up too, by the way. I'll show you the video with them blowing up capacitors on purpose. Huh? So what we do is that, now when something's in motion, it wants to do what? Stay in motion. So what we do on single phase motors is we create a phase shift to start the motor. And then when the motor starts running, we switch that line, we switch that phase shift out. We call that, so what we can do on a capacitive start motor is the start winding is not very expensive. It's not made to stay in the circuit very long, so we don't have to have a lot of copper in it, right? You understand that? So these guys here have a centrifugal clutch on them, and when they come up, you hear it click. You can actually hear these things click when you start them. And then that's when they switch that start capacitor out. So this is a capacitive start motor. Now, these guys here, we have what we call a capacitive start motor. So it's got a centrifugal switching. Now, when the motor starts running, we have a run winding, which has voltage across it all the time. And then what do we do? It's got a start winding, and then it's got a capacitor, and as soon as the motor starts running, it does what? Fix it out. Then we have what we call a capacitive run motor, which is kind of misleading. It has two capacitors on it. One of them they leave in all the time. One of them they kick out. So your start winding has to be made better than this guy over here. So these guys right here are more expensive. They create better run torque and they're for a smaller size. So capacitive run motors will be smaller for the same horsepower than a capacitive start motor. So we got good starting torque, 4-speed regulation, cheaper than a capacitive run motor. Good starting torque, good running torque, size ratio, lift speed regulation, smaller size for the same horse. So you'll see them use these capacitive run motors when they're limited to amount of space they have available to mount them. So this is a typical capacitive motor. Now a lot of motors, especially in HVAC systems, the capacitor won't be mounted on the motor; it'll be mounted out on somewhere. So a lot of your motors have external start capacitors. So your air conditioning system will have an external start capacitor. It'll be 2 ground wires coming out of the motor, and that'll go to the start capacitor. We'll look at split phase motors, which is we use a lot of motors. Them are really cheap. They don't create a lot of start. So this guy here has 200 to 400% of full load current, lower starting current, workhorse and general purpose motors. So we can run it these guys all. This is compared to a split phase motor. Okay. So this is a dual capacitor motor. A lot of them, by the way, like I said, the actual capacitors won't be mounted on the motor. They'll be mounted external. And it might look like it's got one capacitor, but you look, it's got 3 wires connected to it. Because notice your start capacitor, it has a common. I can put 2 capacitors out there, right? Understand. Run how many wires? 1, 2, 3, right? So if you see a capacitor that's got 3 wires coming to it, that's probably a capacitive run motor. If you only got 2 wires coming to it, it's probably a capacitive start motor, right? That makes sense? Are you okay? I think a compressor used in most HVAC systems is a capacitive run motor because they're limited to the amount of size that they have. The motor's actually inside that chain, inside the compressor. Huh? Yeah. There's a video with somebody opening one up. A split phase motor gets a phase shift out of an inductor. Now an inductor is nothing but a bunch of coils of wire. Now inductors has no AC flowing through it, but any DC component will flow through it. So because it's nothing but a bunch of coils of wire, it uses a technique called mutual induction. So we use these a lot. The problem with fluorescent bulbs is that once you shoot that electron through there and it starts glowing, the resistance of the bulb automatically starts going down. And then it would get brighter, which would make it get hotter, and the resistance would go down. Then it would get brighter, it would get hotter, and the resistance would go down. So these guys right here would self-destruct after a little while, unless we put something that would limit the current flow into it. But we don't want that. We don't want that to limit the current flow with a resistor, right? Because the resistor does electrical work. It creates watts. Inductors don't create watts. So we use a thing called a balance. Have y'all heard of a balance? That's all it is just an inductor. So what it does, it creates an opposition because current don't flow through it. They flow what? In and out of it. And they shouldn't get real hot, even though some of them do. You can tell when they're starting getting bad. So inductors, which is nothing but, takes a lot of coils of wire. Inductors can create phase shifts too. So this is what we call split phase motor. It's using an inductor to create phase shift. Less expensive than capacitor motors, very low horsepower, very low starting torque, high starting current, single voltage, primarily used for grinders, small fans, and blowers. So if you got a bench grinder, it's probably got a split phase motor on it. That's why you don't hear it click. If it's got a capacitor motor on it, it's gonna have a split phase motor. Permanent split phase motors are used a lot. So okay? Any questions here? Yay, nay? Shady pole motor. All my stuff is over there. We could do this. We could go over and take the pencil sharpener apart. The pencil sharpener next door uses a split phase. Uses a Chevy pole motor. But what they do is, see the coils of wire here? This is wrapped around 1 to 2. This creates an inductor, sort of like a shorted transformer. So when this AC goes out, it induces the voltage into this, and the voltage it induces into the shaded coil pole is 180 degrees out of phase. Now these guys here are very low torque, but they're really, really cheap. So a lot of fans have them in there. Pencil sharpeners have it, or electric pencil sharpeners have them in there. We got to figure out what's wrong with it. Now, this guy here, to reverse it, how do you reverse it? You literally have to take the shaded pole off, the stab. You have to pull it off and turn that around and reverse that. So we don't reverse these things at all. Yeah, we had a clock in Japan that ran a shaded pole motor. And, we took it out and flipped it around and painted the clock yellow and put the numbers on there backwards. It's the funniest thing. People come in there, get that double click. That's what we did in Japan. We did other things with it. We took a lot of clocks apart. So this guy here is hard to reverse. We can't reverse it. So you have to mechanically reverse this thing. Because most of the time you don't want your pencil sharpener to run backwards, right? So what we do, I should have, how do we reverse the single phase motor? We got to change one of these. One thing. So back in motor control, we got back there, I got a single phase motor and I put L1, L2 in there. The motor run one way. I swapped them. What did it do? Run the same direction. Exact same direction. I could take we hooked up a DC motor and I swapped the plus and minus out here and it run in the same direction. Because what I was doing is I was changing the voltage on the field and the armature. Right? You understand it? Which is weird. You can go over there and now we don't have that problem with a permanent magnet motor because you only got 2 wires coming out of it. You don't have control of the field. So to change the direction of a DC motor, we leave the field alone and change the connection on the armature. That way, if you screw it up, the motor won't run. Right? You understand that? So on a single phase motor, if I came out here and swapped L1, if I came out here and swapped these 2 right here, what's the motor going to do? It's going to do something. It's going to keep running in the same direction. So what you have to do to change these things, the DC and the AC motors, you got to change one of these fields. So what's the industry standard for reversing a single phase motor? We don't have an armature in a single phase. In AC motors, we call the stationary field, it's called the stator. And the rotating field, we call it the rotor. So it's real straightforward. Stationary, stator, rotating, rotor. DC, technically, we call the rotating field the armature, and the stationary field, we call it the field, right? So it's pretty straightforward too. It's just that armature stuff. So what we got to do is so we can't change, we could change the rotor. That would be possible. So we got to change one of these fields. We got to change the connection on one of these fields, either on the Y. The run winding or on the Y. Start winding. So what's the industry standard? Start winding. That's exactly right. So we change the connection on the start winding. Are you okay? Three-phase motors. We don't have to worry about three-phase motors. This is a neat slide. They gave the vector. I think this is the vector. Oh, this is the vector sum of all three phases. This shows how they actually work. It's really, really neat. Notice this guy right here is Thompson what? So this vector right here is moving. What's the rotor going to do? It's going to do what? It's going to move, right? You understand that? So three-phase automatically generates a rotating field. So that means we don't have, so three-phase motors are more efficient than single-phase motors. And they create a real good run torque, a real good starting torque. But what's the big advantage or disadvantage of three-phase? Of course, I gave you all the advantage. What's the biggest disadvantage of three-phase? That's it. That's the big thing. The whole three-phase system costs a lot more than a single-phase. But if I'm going to use a lot of power, then they're more efficient, right? You understand that? So how do we change the direction of a common three-phase?
Change
Industry standard. Over here.
change L1 and L2.
L1 and L3. So literally, how can you reverse? So you got to watch out for those kind of questions. They do that on the Siemens test. It says, how can you reverse a three-phase motor? They don't ask you the industry standard. Okay, so how can you reverse a three-phase motor? Well, you can swap any two phases, right? You could literally swap 1 and 3, 2 and 3, or 1 and 2, and the motor would reverse.
Probably expect
What do you mean? Yeah, but we're talking about three-phase motors. You're talking about single-phase loads. So when we was in motor controls, what we tried to do, when you hooked up your transformer, we tried to get y'all to use different phases on the transformer for your single-phase loads. What you're trying to do is you're trying to balance the loads on your three phases. Well, a three-phase motor is a balanced load anyway. Okay, so you're not concerned with so I'm trying to run single-phase loads. So in off three-phase, well, normally what we do is we come to the transformer. But what you're trying to do is you're trying to balance the load. You want to keep your loads balanced on the three phases. Do you understand what we're saying? Yes or no? It's just like on your house. Your house, you should stagger your circuit breakers on your house, so you won't overload one side of your transformer out there on your pole, your single phase. Your 240 loads, you don't worry about those because those are both off on both sides of the transformer. Your 120 volt loads are either on one side of the transformer or the other side of the transformer. Understand what I'm saying? I can't get to my marker. My pause is right on top of my marker. Control the speed of an AC motor. So primary speed. So it's not normally controlled with what? Focus. Focus is lowered, both speed and torque increases. Both focus increase, the load rate both torque increases, the speed rate increases. One thing we don't want to do is if I'm trying to run a 5 horsepower load, I don't want my motor to produce more than 5 horsepower. Okay, you understand that? So we'd like the torque to be fairly constant. The speed that the stator field is rotating is calculated by this guy. So according to this, we can change the speed 2 different ways. By changing the number of poles or changing the frequency. So what you're doing on your ceiling fan, when you change the speed, you're changing the number of what? Poles. That's what you're doing. You're flipping in different poles, arrangements. And then, of course, the more poles you add, the slower it runs. The less poles you add, the faster it runs. Of course, the minimum poles you can have is what? 2. And you have to go in pairs, right? Because you got a north and south pole. So a 2-pole motor, the field will rotate at 3,600 RPM. So what would a 4-pole motor do? Which is very standard. So what would the speed of what would be the speed of the field for a 4-pole motor? Oh, y'all paying attention? What would be the what would be the field speed for a 4-pole motor? Alabama Power. Alabama Power, what's our frequency? 60 Hz. So what would be the field speed of a 4-pole motor? 1,800 RPM. So you over on the lab, you look at all of them, they're rated like 1725. The rotor of these are called induction motors, so the rotor can never ever run at the same speed as the field. So the speed of the rotor is 120 divided by the frequency, divided by the number of times the frequency minus the slip, how much slip the motor has. So every induction motor has to have what? So we don't use the voltage because the voltage would change the torque of the motor, right? You understand? If I lower the voltage, I could get down real fast where it could do what? The motor would stop. If I increase the voltage, the motor won't speed up, right? You understand that once it gets to its rated speed, the motor won't speed up, but your torque will change. And the motor's going to pull a lot more current than it's supposed to pull. So speed can be changed by changing the number of poles. Speed can be changed by the problem we have with changing just the frequency, or I've got an inductor. So what's the problem with just changing the frequency? All that has AC. Wait. Or take it. You've already got the formulas. You've already got the formulas for inductors and you've got the formulas for capacitors. Okay, but you had the formula for capacitor. And the motor is primarily one of these. This is a inductor, right? Let me give y'all the formula. Anybody had AC? What's the formula for inductors? What's the formula for capacitor? Something. So we have opposition. We call it reactance. We abbreviate this. This is reactance. And then reactant means it reacts to frequency, right? You understand that? And so capacitive reactance, we call that X sub C. Okay, guys, AC. This is a formula you should know. Shouldn't have to use a formula sheet for this guy. Let's take 1 over 2 pi SC. And what's 2 pi? Normally 2 pi we use 6.28. Frequency, what's L? Well, Alabama Power, this is the frequency. And then this is the capacitance. What is the capacitance, guys? Yeah, that's what it's in. But what is the capacitance? What is it? It's the storage capabilities of the capacitor. So the more C it has, the more coulombs it can store, right? You understand that? Right? Y'all understand that? The less C it has, the less storage capacity it has. So a small capacitor would have more opposition than a big capacitor, not physical, y'all understand that? But what we got in that equation is we got that dang F right there. What is that? Frequency. So what does that mean? It means that opposition, a capacitor to the opposition changes with frequency. Now, X sub L, inductors are just opposite of capacitors. So if we took the reciprocal of that, meaning opposite, then this is a capacitor right here. And L is the ability to store a what? To store a charge. But it does just opposite of a capacitor. So when a capacitor is charging, an inductor is discharging. If they were in the same circuit, which is pretty neat. So this is what a motor has right here. A motor has a what? Yeah, got an L. That's what a coil of wire is. So there's the inductive proximity sensors we went over way back. Wait. How does a what? How does an electric fence work? No, well, it could be. You got to be able to voltage up. Normally, what they do is it runs off of a DC pulse, is what it is. And normally, the time how often it pops, it probably uses a timing circuit, a capacitor resistor. But it usually goes to a transformer. It has a transformer that sets the voltage way up. Now, electrocution depends on a lot of stuff. It depends on how much current you get into and how long you're into it. Right? So what does electric fence do? It's not charged all the time. The ones that we have, it does what? I'm laughing. We had a guy worked out at U.S. Steel, worked over in Inslee, and he wanted us to increase the voltage output on his fence, his electric fence. So we got in there and we worked on it, moved some stuff around. I don't forgot what we got it up to. It was so funny. So he got over there, and they were their shop was solid metal shop on concrete. Yeah. So he got in there. It was so funny. We were in there. And he said he was going to be real cute, and he got over there and put that thing around the doorknob, and then put the other charge out on the floor mat. You know what he did? He went back there and sat down. And he was just laughing, and he leaned up against it and zapped himself. We had this is true too. We had a bunch of radio controlled gate openers that we were responsible for maintaining. And we brought a car coil in there, the old car coil that would step 12 volts up to over 45,000 volts. And we drove a nail up in a chair. So it just barely touched. Come out the bottom of the chair. Mounted that coil up under there, and then put that gate opener on there so we could trigger this thing. And we put some crane batteries under there, about 12 volts under there. We strapped all together. But you could trigger that thing with the remote control with that gate opener. And it was so funny. You'd get people that come in and sit down in that chair. You start doing that. And then they'd get up and say, man, I'm sitting on a nail or something. But we had one guy one time, he come over there, and he was leaning over a tiny shoe. And we bopped him, and he flipped out that thing on his head. It was so funny. But we came up, we did a lot of things. That's a true story. We put a backup warning device in an old function generator, one of these things. And it was a big old thing. And it was a backup warning device that they put on those big old tractors out there. You know, them suckers are loud. And we put a timer on it and had it set to go off at 4 o'clock in the morning. And when you work maintenance and you don't have anything to do, you know what you do at night? You sleep. And that thing made the rounds. But we put a hole in the back of it, so if you took your time, you could go in there and figure it out how to turn it off, because it ran off a battery. Right. But we had one guy, we called him Shiny, because he was bald. But he wore a toupee that snapped on his head.
Oh, toupee.
Yeah, he glued these snaps on his head. It snapped that thing on his head. But we called him Shiny. Everybody called him Shiny. Everybody knew he was bald. And Shiny got in there and couldn't figure out how to do it, and he got him a crowbar. Tore our alarm apart. So 2 pi FL. So what happens when you change the frequency on that? So it looks like I can change the frequency on these things, right? But what if I change the frequency on an AC motor? Well, if I change the frequency, I change the opposition. XFL is opposition to AC called by coils of wire and on. Frequency to be applied, AC frequency applied, AC voltage. L is the adjustment of the coil of wire and heat. If the frequency of an AC motor is changed, its opposition changes. If frequency goes up, the opposition goes up, and torque goes down. Frequency goes down, opposition goes down, and torque goes up. So we don't want torque to go down, because what happens if torque goes down? What could happen? The motor could stop. What happens if torque goes up? You could tear up what it's running, right? You understand that. So what does that mean? We don't change the speed of an AC motor. We got 2 ways. We can change the pole or control the speed without changing the torque required both the what? Both the what? Voltage and the what? Frequency change proportionally in the same way. It's called volts per Hertz ratio. All you have to do is look at the voltage rating on the motor, frequency rating, divide them out, and that'll give you what you call a volts per Hertz. So that's one of the things you do when you program a variable speed AC drive is you enter the voltage and you enter the hertz, and the thing does what? It does the math for you. So basically what you do is you just enter that information that's on, anybody ever programmed a variable speed drive? Most of the time you just take the information that's on the faceplate and then punch that into the thing. And then of course you've got other things you can do. You can set up the acceleration rate, how fast it accelerates. You got a big horsepower motor and you start them suckers across the line. Well, yeah, 6 to 8 times its full run torque. So you got a 100 horsepower motor, you turn that sucker loose starting it up, that sucker could generate 600-700 horsepower of power. What could it do? It'd tear some stuff up, yeah. So we used to deliberately lower the voltage while the thing started. We call them reduced voltage starters. So you run it through resistors or you run it through inductors, and then when the motor starts running, then you switch it over when it's already running. So reduced voltage starters. A variable speed drive will do that for you. You put the acceleration on that thing, you say I want to accelerate this percent, and it will literally keep a constant torque. It'll start at the same torque and move it up, and it's really, really neat. So you got a lot of options that you program to one of those things. Thomas has a book on one. What they do is they use a technique called pulse width modulation. Notice what they can do. Not only can they change the voltage, but if they come in and start reducing the valve, what are they going to do? They're going to change the frequency. So normally these things use pulse width modulation. Variable speed drives. I couldn't find one that changed the frequency, but I thought this was real neat. Your AC motor will see this. Your AC motor's got a big inductor on it. We won't quite see that. If we fed this thing directly to it, we would end up with a I still can't get to it. I never can get this one to work. All I do is get this. I can't get to my marker down here. See, my pause thing is right. I don't know why it does this to me. Go see what I can't get to my marker. There we go. So what we would actually end up with, we'd end up with something that was, yeah, I'll take that. Why can't I get this thing? There we go.